Hello everyone, myself Pushpilata, Assistant Professor, Department of Electronics and Communication Engineering, SJBIT. Today we are going to discuss some of the topics which is related to Module 2 of VTU syllabus, and it comprises of the 8051 instruction set contents. And we are going to talk about the logical operations, arithmetic operations, and jump operations with respect to the 8051 microcontroller. When we talk about the microcontroller, the central part of the microcontroller is the computation unit, that we call it as arithmetic logic unit, ALU. The ALU is responsible for basic mathematical computations such as addition, subtraction, multiplication, and division. And basically the ability of this 8051 is to perform arithmetic operations on 8-bit numbers. So we are going to discuss about the 8-bit number operations using 8051 instruction set. And yes, the ability of 8051, that means the architecture of 8051 itself provides a necessary flags such as carry flag, auxiliary carry flag, overflow flag to handle all these mathematical operations. In addition to this arithmetic computations, the instruction set of the 8051 has logical operations that work on bit operands as well as the byte operands. And we are going to see all these things in depth with respect to the coming topics. So let us discuss about the logical operations first. Consider the logical operations. We talk in terms of binary logic. So binary logic defines the value 0 as low value and 1 as the logic level high. Right? So any electronic circuit, it normally defines the binary value 0, which is equivalent to 0 volts, and binary value 1, which is equivalent to 5 volts. So hence, using the transistors as the building blocks, we make use of several electronic circuits, and that using the gates which are designed. And the property of these gates is basically that there are one or more logic level inputs. Okay, uh, and similarly there is one logic level output. Okay, so when we talk about the logic gates which are based on these binary arithmetic operations, the binary arithmetic uh, operators, okay, they are something like and, or, XOR, not. Okay, so these are the fundamental basic elements, okay, of any particular logic gates. And to discuss about these arithmetic operators and corresponding gates, we have certain instructions to follow. To begin with, AND gate is based on this operator which has two logical inputs, say that A and B, and one logical output Y. Okay, so the output of this logic is high or 1 only when both the inputs are at logic level high. Okay, and the output of this logic level is 0 for all other conditions or whenever any one of the input is 0. Right, so with this particular logic, okay, the AND gate is analyzed, right? And similarly we have OR operation where the OR gate is based on the logical addition of the inputs, right? So when we talk about the OR gate, we have 2 input, 3 input. Okay, so if we generalize it for 2 input, okay, we also have 2 inputs like AB and Y for OR gate. And if one of the input of the OR gate is at logic high, the output will be high. And if both the inputs are at logic 0, then only the result will be 0. right? And we have one more gate that is called as XOR gate, and this XOR gate we also call it as exclusive OR gate. Okay, the symbolize is like this, and here also we can see that having two inputs like AB and output is Y. It is an exclusive OR operation. The output of the XOR gate is a logic high only if one of the two inputs is at logic high, if at all. Okay, it is any one of the input is at logic high, then the output is high. Otherwise, if both are similar inputs, the result will be 0. That is, if at all 0 0, the result is 0. 1 1 is also a result is 0. And the last we have a NOT gate operation, which is also called as an inverter, which complements whatever the input logic you apply for the specific gate. And the symbolized symbol representation of this is something like this. So whatever the input you give, it will be complemented A bar, and that is, you call it as NOT of A. And likewise we have some more gates like NOR gate, NAND gate. Okay, and those are termed to be the universal gates. Okay, we try to make use of those with respect to performing all other operations. In 8051, we represent the instruction as ANL for AND operation, ORL, that is OR logically for OR operation, XORL, that is exclusive OR logically for XOR operation, and CPL for complementing or for the purpose of NOT gate operation. Similarly, for rotate instructions, we have RL, which rotates the byte to the left. The most significant bit becomes the least significant bit. In case of RLC, it is rotate left through carry. So we are going to rotate a byte and the carry bit to the left. The carry becomes the LSB in this case, and MSB becomes the carry. And the next instruction is RR, that is rotate a byte to the right. Here the LSB becomes the MSB. One more instruction we have RRC, that is rotate a byte right to the through the carry. So we are rotating a byte and the carry to the right. The LSB becomes the carry and the carry becomes the MSB. Swap is an instruction which exchanges the lower and higher nibbles of a byte. Okay, so if you have a byte, then the lower and the okay, let me write it as 7 8. Okay, 8 becomes 7, 7 becomes 8. So it is going to swap the lower nibbles of a byte. Next, we'll discuss about the byte level logical instructions. When we talk about the byte level logical instructions, we have AND gate as a first instruction to discuss. ANL A comma hash N. So here ANL is, we are ANDing the contents of the source and destination. Here the source is an immediate value, destination is the content of an accumulator. So we are ANDing each bit of the accumulator with the same bit of the immediate number N, and we are dropping the results in the accumulator, that is the destination location. In the next instruction, we are ANDing each bit of accumulator with the same bit of the address, direct RAM address which is mentioned. The RAM address contains the data, and that particular bit will be ANDed with the accumulator and put the results in the accumulator. Next, we have ANDing accumulator content with the register content. Next instruction is where ANDing accumulator with the content of the register, with the content of the RAM address contained in the RP, and finally load the result in the accumulator. And next is ANDing the direct RAM address with the each bit of accumulator and store the result in the address location. In the last we have ANDing the RAM address with the immediate value number. Finally store the result in the address location. And this is with respect to the OR operation. So with respect to the OR operation, the logical OR instructions operate on a byte-wide operands, and one of which we make use of again accumulator. The results are stored in accumulator, and these instructions basically they are used to turn a specific bit into a register without affecting other bits. Okay, say for example we have something called as ORL P0 comma hash 01H. So in this case what happens is we are making a bit 0 of the port 0 register. Okay, uh, uh, which go to the logical high state. That means, say for example, port 0, the bit P0 bit is 0, and when you load this 0 1 to that particular location, it will be loaded with 1 or transformed to 1. The other bits of that port 0 will not be affected by this particular instruction. So whenever we are turning on a specific bit, we can make use of this register. And some of the examples of OR gates are mentioned here. ORL is the command which logically ORs the content of accumulator with the immediate value and store the result in the accumulator. Similarly, we have ORL A comma address. Here we are ORing each bit of accumulator with the same bit of the direct RAM address and store the result in the accumulator. ORL A comma RR. Here we are ORing the content of accumulator with the content, same bit of register R. Store the result in accumulator. And this we are ORing the content of A with the content of the register. Okay, because the register contains some address and the content of the RAM address. Okay, the content of the, we are ORing the accumulator content with the content of the RAM address contained in the register R and put the result in the accumulator. We have one more instruction ORL where it ORs the address with the accumulator content and store the result in the address location. And ORL address comma hashin, which is going to add the it's nothing but OR is nothing but again adding operation only. So OR the address content with the immediate value and store the results in the address location. These are the instructions which we make use to perform XOR operations. These logical exclusive OR instructions, they operate on byte instructions. One usually you can also call it as accumulator, and with all other immediate value, address, register, indirect. Okay, and also you can make the destination as an address with an accumulator as a source and immediate value as a source. So as we have discussed, all these will perform the XORing of the content of source and destination and finally stores the result in the destination location. We have one more instruction which we call it as CLRA. It clears each bit of the A register to 0, and CPLA, it complements each bit of the accumulator. Like if you have 1, it becomes 0. If it is having A 0, it becomes 1. So each bit will be taken as a complement. Next, we have some bit level logical operations. to discuss. When we talk about the bit level logical operations, there are specific memory address locations which are allocated for performing the logical bit operations. In 8051 instruction set, it allows the modification of even the individual bits using these logical instructions. Okay, so the logical bit operations, they are most convenient for controlling some of the peripherals, like we have timers, interrupts. Okay, so many like that, if at all we want to operate on a single bit, so that time we make use of this kind of logical bit operations. And only certain SFR registers, they allow the logical bit operations. Not all the SFRs will allow the operations. And when we talk about the memory space, the RAM address space defined from 20 to 2F. Okay, so these are the mapped bit registers starting from 00 to 7FH. Okay, and this table shows the RAM space that can be addressed as bytes or even the bits. Okay, this 20 is a byte address and 00207 is the bit address of that particular byte location which we are mentioning. That means the 8-bit of byte address, okay, are mapped to the bit addresses, that is 00 to 07. Similarly, 21 is the address which is mapped to 08 to 0FH. Okay, so likewise we are mapping the individual bits and we can manipulate or perform some operations using this bit level address. Okay, and we have some list of special function registers and their bit addresses. Okay, so all these SFR, what we are showing in the table, they have their last 3 bits equal to 0, and the bit addresses are derived by adding the bit number, that is we have something called as 0 to 7 to that byte SFR address. Okay, say let me call, I have something like port 0.3. Okay, and the address of this you call it as ATH. Okay, and if at all I want a specific location of a bit, what I'm supposed to do, ATH corresponds to port 0, but I want port 0.3, that means third bit of the port 3, sorry, port 0. In that case I need to add 80 with 3, so this points to 83H. Okay, so the specific bit will be pointed, and note that the addresses of these least significant bit is the same as the byte address. Okay, and as I told you, some of the special function registers with the direct address and the bit address are mentioned in the table, where we have A register with the direct address is 0 is 0, and bit address if we take E0 E1 up to E7. Similarly, B register, the address is 0F0 and F0 to F7. Likewise, we have mentioned all the direct addresses of the special function registers. As I told you, all SFRs will not support for the bit address. So which and all will support for the bit addresses is A, B, IE, IP, that is interrupt enable, interpriority, all the ports, then program status word, timer control and serial control. So these are the SFRs which are supportive for the bit addresses. Now to talk about the bit level Boolean operations, these are listed in this particular table. So most of the instructions, they use the carry flag, which is bit number 7 in the program status word register, that is PSW. Okay, so that is a bit number 7 which makes use of a carry flag. And bit instructions are quite more powerful in using the 8051 basically for port output operations. whenever we want to like setting or clearing the port pins, okay, or port outputs at regular intervals of time, and you want to generate some square waveforms that are used to turn on the relays and transistors in power electronic circuits. In that situations, bit instructions are quite more useful. Similarly, whenever we are performing the arithmetic operations, that carry flag is checked for overflow from byte operations. So that case we can make use of this kind of bit level Boolean operations. Now to have a description, some of the bit level Boolean operations are shown. Here it is ANL C comma B. So what we are doing, we are ANDing the content of C with the addressed bit. Here B is the addressed bit, and finally drop the result in the destination C. And similarly ANL C comma slash B. So here slash indicates the complement of that particular addressed bit. Okay, if it is 0 or 1, so it is complement of that, and put the result in the C. And OR operations also have the same instructions, and CPLC is the complement the carry flag, CPLB is the complement the address bit, and CLRC is the clear the content of C flag to 0, CLRB is the clear the address bit to 0, and we have move C comma B, where we are copying the address of the bit to the carry flag, and move B comma C, we are going to copy the carry flag to the address bit. Set BC, this is basically which sets the flag to 1, that is the carry flag to 1. Set BB, it sets the addressed bit to 1. So with respect to these bit level operations, we can make use as per the requirement. Next we have rotate and swap instructions. So these are the instructions which work on the accumulator. The rotate instruction is basically used to shift the entire bit pattern in the A register, like if at all we are using the circular buffers. Okay, so accordingly there are we have two types of instructions which rotates the register either to the left or to the right. So to the left we have RL, and to the right we have RR instructions. And a register with or without the carry bit, also we can rotate it. That means like whenever we are rotating the instructions which are distinguished basically by rotating A with or without the carry flag. Okay, so we have these are some of the instructions where rotate RL, that means the content of the register A is rotated to the left, 1 bit position to the left. So what happens now, accumulator is of 8 bit, right? So this is bit 0, bit 1, 2, 3, 4, 5, 6, 7. Let me talk about this is having some value. Okay, now what happens if you are shifting it to the left? Okay, so what happens, it is shifted towards the left, and now 1 bit will be shifted to its, I mean A0 2 will be shifted to A1, and similarly A1 will be shifted to A2, and simultaneously it will shift, and A7 will go to A0. Okay, so this is the left rotation, and yeah, hopefully even right rotation will go in reverse order, that is RRA. Now when we talk about RLCA, it rotates the content of A register along with the carry. So carry flag will be initially maybe 0 or maybe 1. So it depends on the operation what we are performing. So what happens is when you are rotating it to the left, your 8th bit will go to the carry, that is a 9th bit, and from 9th bit it will go to the LSB. That's it. And the reverse operation is the RRC. Next we have swap. I told you it is the interchange of the nibbles of a register. Put the higher nibble in the lower nibble position and lower nibble in the higher nibble position. So these are some of the sketches to show the rotate operations. So this is with respect to the left RLA, and this is RLCA, which is to the carry, and next we have RRA, is taking the right rotation, and RRC, which is taking the right rotation through the carry, and swapping of the higher nibble with the lower nibble, which we make use of a swap instruction. And these are some of the examples where we are taking the accumulator with some value called 0AH. Next, we are rotating 4 times of RR. See, when we make use of RR 4 times, it is as good as we are using the swap instruction 1 time. Rotating right accumulator with 4 times, it is as good as you are swapping the content 1 time. Say for example, I have accumulator A5. After 4 times rotation, it becomes 5A, right? But when I use swap A directly, that 5A becomes A5 back. So rotate operations, rotating 4 times is as good as you are swapping it 1 time. Next we have CLRC, clears the content of carry, okay, C to 0, and RRCA, which rotates the accumulator content right through the carry. So the carry value is now changed because the higher MSB nibble of the accumulator shifted the value to its carry. Next we have RRCA, you can do it the same, again it will do the right rotation to the carry, and rotate left, which rotates the content of accumulator to the left. And yeah, 2 times we are doing it here, swapping. Okay, so all these things are just the examples of rotate instructions. Here we have a program to double the number in a given register. Basically, we are doubling the number of R2 and putting the results in R3, that is higher byte, and R4 with the lower byte. Now initially we are clearing the content of R3 by transferring 00 to R3. Then clear the carry flag. Now what we are doing, the content of R2 is taken to accumulator. We are rotating it left through the carry so that it doubles the number. Once it is doubling the number, the lower byte which is there in the accumulator will be transferred to R4. Then I need to get the carry which is there to the in the carry flag. Carry is there, that I am supposed to take it to accumulator. Since already accumulator is having the lower byte, I need to clear the accumulator. Then again rotate left through carry. Now the carry content will be moved to the bit 0 of accumulator. Then take that accumulator content to R3. Now R3 will be having the higher byte and R4 will be having the lower byte, and the double number is stored in R3 and R4 respectively. Thank you. We'll continue the session in the next.